Hello there, welcome back. Last time we've worked on reading a partition table. We have found our boot partition. So today we will work on writing a FAT16 driver, a minimal one, just to be able to read files off of FAT16 partition. And we will use that to read our config file. So let's get to it. Right, so I guess the first thing I want to do here is to rename this loadgb to something more appropriate. So I'll, let's say, read get boot partition from GPT, something like this. I also want to do something else here. So let me just quickly define a struct, which I'll call partition info. And we'll see if we'll keep this or if we'll just remove it, but for now. So what I want to have here is a partition type, and so U32, I guess, 64 maybe, partition start LBA, and U64 partition and LBA. There we go. So now we need to define partition type. Maybe we can just define some sort of enum partition type. And in here we'll have just EFI system for now. And count. Partition type count. Right. Oh yeah, let's just type this one too. Oops. Partition type. There we go, that should be fine. So this one here should know that it's this one here, and I can also just remove this since it's not used for anything for now. Right, and what I want to do here is I just want this to return a partition info. Right, and right after this I will return and I will do type is well, EFI system and partition start LBA. This would be so what was the, okay, so it's just entry start LBA and partition and LBA. This would be entry. I don't remember what we've called that, so let's see what we have here. So yeah, just call and LBA. Right, so and LBA. Okay. And yeah, of course, I forgot to do partition info. Of course, this needs to be set somewhere. So partition info result, I guess, and we can just do return result. Yeah, we don't really need this. That should be fine. Right. So I just want to check that this one is EU16. This one should be EU16 too. That's cool. Right. So now that we have the result, we should just go ahead and store it somewhere here. So partition info boot partition equals that. And now we can go ahead and I guess read or init our FAT16 driver for our boot partition. Right, so let's go ahead and do that. So for now, I'll just create a FAT16. Just call it fat init, and we'll give it the boot partition. There we go. Okay, so I guess we can go ahead and create this function here. So for now, it returns nothing. At least we are not interested in anything it can return. And of course, it takes a partition info boot partition. And just thinking here, if I want to pass this around by copying it, or if I want to pass it a pointer to it. So I guess I could just pass it a pointer to it. Yeah, that should be fine for now. So let's just do, and probably even add a constant there, just to be safe. Right. So now we know where our partition starts and where it ends. So we will need to go ahead and implement the fat spec. So let's just bring that up. Right. So here we have the spec. So let's just try to fast forward this. Right, so I went ahead and created these structs here. The extended BBP for FAT32, the extended BBP for FAT16, and here this is the main BPB struct. And I've created a union here I call extended, and I've put the two extended structs in there so that we can access them if we need to. So now I guess we should go back to this and start doing what we need to do. So first of all, let's recap what the fat file system looks like on disk. So this is what it looks like. We have a reserved region, which is basically the region that's occupied by the BPB struct. Then we have the fat region, and here we have the fat file allocation table, and we can have a copy of the fat optionally, but I think we have it on our disk image. So and right next to this fat region, at least for FAT12 and FAT16, we have a root directory region adjacent to it. And after that, we have the data for the files and other directories that we might have in our root directory. So for FAT32, the root directory is actually given by a field in the extended BBP for FAT32, but we don't really care about that for now. So we will just assume that we have our root directory somewhere near our fat. Right, so what we want to do is we want to first check that we are actually in FAT16, and for that we are going to use this mechanic here that's described in section 3.5. So we will count the number of clusters that we have, and if the number is above this and below, or rather is above this and below this, then we should be in FAT16 and we can continue. Otherwise, we'll just spit out an error. And then what we need to do is we will need to load our file allocation table, because we will spend a lot of time working this file allocation table. So we'll need to read it and pre-cache it. And then we will probably also read the root directory and pre-cache it so that we can have easy access to the contents of it. So let's do that, and we'll see where we go from here. Right, so we will apply exactly what we are told to do in the spec. So first of all, we'll need to determine the size of a FAT table. So for that, we need to get, well, actually, before we do that, we will probably just need to read our partition to somewhere in memory, right? So let's first start by doing that. And here, what we need to do is just allocate some memory. So BPB, something like this, and we'll call it BPB also, or BPB. Yeah, well, this is why I didn't want to call it BPB. Right, so let's rename it to something else. Right, so BIOS param block. Cool. And with this, now we can just go ahead and call this BIOS param block. Oops. Block. And so BIOS param block, and here we are going to basically allocate a bit of memory. So let's BIOS param block pointer, and here we are going to call PM alloc. For the size, I guess we can just allocate for size of BIOS param block, and for the type, I forgot about the type, we can just mark it as reclaimable. Okay, so now that we have this, we can basically do the same thing that we did here before, and we can just probably just yank this from here and just add it here. Here we can give it the BPB, and for the count, I will just ask for just one. Yeah, just one would be enough. For the start sector here, we can go ahead and just take boot partition. So start LBA. There we go. And of course, here we might also need to check something. We need to do if boot partition type, I guess, is different from EFE system. Yeah, we can do something like this. Then we just go ahead and printf some error. There we go. Okay, so probably just add this. Nice. Okay, so now we have read our BPB, so we can probably just start and print in some information about this. Right, so what do we want to print? So BPB. So let's start by first doing this, and this, and we'll see what we have here. What's interesting here? I think bytes per sector is interesting. We can also have root entry count, I guess. And probably total sector 16. Right, so what is this? This is a U16. This is a U16, and this is a U16. So let's go ahead and do this. So we'll just print them as ints. So BPS equals that. REC equals that, and this TS16. This would be that. There we go. Here probably just yeah, do this just to avoid some weird issues with the compiler, but it should be fine. All right, so let's run this and see what we have first. Right, so here we go. So now we can see that the values are 1026, 63, 560, and 20. These values look off to me. So what I will try to do is just dump the disk image and see what we can get from there manually. All right, so let's see what we have here. So I guess these three bytes here are the jump boot thing, and this string here, which spells makefs.fat, is our OEM name. And right after the OEM name, so if we go back to the definition of this, right after the OEM name, we have bytes per sector. And here, bytes per sector should be these 2 bytes. And for me, this spells 200, so it should be 512. So I'm thinking that maybe, let me check something. 3, 8. Okay, I think that maybe the compiler is playing tricks. So let me just tell it to not touch my structs. So attribute backed. Right, so the compiler will try to reorder the structs to have the best backend possible while keeping every entry aligned to its own, I guess, alignment standards. So, but here we know that we get this struct at exactly this format here. So we should keep the back nature of the struct. So let's try to go again, compile this, and see what we get. All right, so let's run this again. And it looks a lot more sane to me. BPS 512, rec 512, and TS 18 something. Yeah, that looks good. That looks pretty good to me. Just to be sure of this, I actually found a very cool utility. So this is a cool utility called Kaitai. I guess that's how you pronounce that. And you basically describe in some sort of DSL the binary format that you want, and you give it a image or a file that has that format, and you can basically just inspect the format here as a tree, and we can see here that bytes per sector, or ls here is for sector, so it's 200, which is 512. That's what we had, and max root dir rec is our root directory count. It's also 512, and what was the other thing that we've printed? I think it was it was this. I think total sectors. Well, the names are different on this format I found, but I guess it was this, and it was 18,432, which is these 2 bytes here. So I think for now we have this working. So let's go back to code. Right, so now we have this. We can probably just get rid of these. We don't need them anymore. Right, so now what we need to do first is try to figure out if we are actually reading a FAT16 partition. And for that, again, we should go ahead and follow the spec. The spec says to first determine the count of sectors occupied by the root directory, and we have here a nice formula for that. Right, so this is the number of entries in the root directory times 32. I guess that's the size of every entry. And we, so what they're doing here is they're getting the number rounded up of bytes per sector in this size here. So this can be something that we can write as a helper. So let's do that. So here, and this would be like U32, I guess. So root dir sectors, and this would be, so let me just check. So it's the BPB root entry count times 32, but we get what do we call this? N upper, and this will take 2 things, and this will be bytes per sector. Yeah. There we go. And this N upper will basically give us the rounded up number of, or basically the rounded up result of this division of this by this. So let's write that. And I think we have this here, and we have a line up in there. So we can just add this right next to it, upper. And this also would take a X and a Y. And we will return X plus Y minus 1. And so I should probably do this. Y minus 1, and we divide that by Y. And we should probably just do something like this. Maybe even, there we go. Okay, so now if we go back here, we should probably just go ahead and import or include bitmath. There we go. And now if we take a look at this, we can see that we have the macro expansion. It expands to basically what we wanted. So this times 32 plus that divided by the bytes per sector. So that's fine. Right. So now we have the root directory. So that's that's done. Next, we need to determine the count of sectors in the data region. Right, so I guess we need something called fat size, in which we will put the fat size 16 if it's not 0, otherwise fat size 32. Let's start doing that. Right, so U32 fat size, and this would be 0. And if yeah, I guess we'll init it right away, so there's no need to do that. And this would be fat. So I think I've called this table size 16. So if this is different from 0, we go ahead and put fat size equals bvp dot table size 16. Otherwise, this would be fat size would be bvp table right. Otherwise, here we are going to put extended there we go, extended fat 32, and I think we have something that's table size 32. There we go. So that's for the fat size. Now let's take a look at the documentation, and here we are asked to compute the total number of sectors. Okay, so that's that should be easy. So U32 total sectors, and if BBB total sectors 16 is different from 0, so we use that. So total sectors would be BBB total sectors 16. Otherwise, we will use total sectors BBB total sectors 32. There we go. And now I guess the final step would be to determine the data sectors, and it will be the total number of sectors minus the reserved sectors, the number of fats times the fat size, and the root directory sectors. Okay, right, so this was U32 data sectors, and this would be total sectors minus all the reserved sectors, which are BBB reserved sector count, and the fat size multiplied by BBB fat, what did I call that number? Was it table count? I guess table count, yeah. Is what I called that, and then we add to that the root directory sectors. There we go. And with this, we have our number of data sectors. And now what we want to do is we want to know how many clusters we have. So U32 cluster count, and this would be the data sectors divided by BBB sectors per cluster. There we go. Okay, so now we have the cluster count. So we need to ensure something. And actually what we need to do here before this is there are some computations that we will need to do over and over again. So let me just create some inline functions for them. And I guess inline U32 root directory sectors. And this one takes a BIOS param block pointer, a const one actually. And call it BBB. And here we are going to just basically yank this into here and return root dir sectors. And of course, just use it here in its place. So this would be root directory sectors and give it BBB. There we go. Okay, and now I guess we should also do the same here. So inline u32 fat size. This would take a const block pointer. Oops, there we go. Right, so let's just block this out and here and return fat size. There we go. And of course we have another one. So inline UE2, and that would be total sectors, and it takes a const block BBB, and so I guess we can already just replace all this with fat sectors of BBB. Oh, fat size, sorry. And I guess we can just do something like this. There we go. This one is not used, so let's just do it manually. And this one here will be get fat size. There we go. And now we just block this out. So yank that, go there, paste that. Oops. There we go. And of course we return total sectors. And I guess the final thing that we want to have is this data sectors. Actually, I'm not sure how often we'll use data sectors or even total sectors, but at least root directory and fat size are very useful. So for now, let's leave these two there, and now we will just go ahead and add our check. So if so we are checking that we are not in FAT16, so the cluster count is less than, and I don't have the number, so let me just go and check it for yeah, so 4085. So 4085. So if we are less than that or more than so 5, just copy that. I'm gonna remember it. Or equal actually. So larger or equal to that. Then we are definitely not in FAT16. So we should not handle this for now. So error. Okay, and we should probably just return from this, or probably just spin. Yeah, should be fine. Otherwise, we have a valid FAT16 partition, so we can start working with it. All right, so now we should read our FAT file allocation table. And for that, we need a few... Oh, we actually already have the FAT size. So we know how big a FAT table is, and we know where it starts because we know that it starts right after the reserved sectors. So I guess we can just define that here. FAT start, and this would be... or maybe we can just even get the start LBA for that. And this will be, actually, let's first just get the start relative to a number of bytes. And this will be bbb.reserved reserved sector count times, well, that should be it, I guess. So if we take that and we add to it boot partition start LBA plus, there we go, something like this. This here would be the LBA of the start of the FAT file allocation table. Of course, this one is a U64, but we will just cast it down to U32. There we go. So now we can just issue a read call for this file allocation table. But first of all, we kind of need to know what the file allocation table looks like. And for that, let's go back to our Katai thing here. And from this, we can see that the file allocation table is basically just for, at least for FAT16, it's 16 bits wide. So it's 2 bytes. Every 2 bytes is an entry of the FAT16 FAT, basically. In FAT32, it's 32 bits, so 4 bytes. And in FAT12, it's just 3 tetrads, or 12 bytes, 12 bits. Right, so I guess we can just go back to code now and just define a U16 pointer to be our FAT, and then we can just issue an allocation here. So U16 pointer of PM alloc. And here we know the size of that, which is FAT size. Right. And the type of this is, of course, reclaimable. We are going to need to clean up everything after we are done with this. And here we issue the BIOS read sectors, and we can now tell it that we have a start LBA. We have a U32. What did I call that? FAT. You called me fat. Right. And we need a count. So the count is a number of sectors. We have the size of the FAT in terms of bytes. So I guess we can just align up the number of sectors to the number of, or rather the number of bytes to, actually it's not align up that we need, it's n upper. And here we need to give it fat size, and here we need to give it arc page size. No, sector size. There we go. There we go. And are we still missing something here? Expect, of course, we are missing this. And this should be fine, I guess. What's fat size? Fat size is U32. All right. You know what? That should be fine. Right. So now I guess we can just go ahead and print a few things from our fat table and compare them to what we are expecting. And let's see. So I guess we can just print bytes. So let's print a few of those. About 4 of those. There we go. Right, and here we are going to do fat 0, fat 1, fat 2, and fat 3. Okay, so let's build this and see what we have. Here we can see that we have the first fat entry is F8. So if we compare that to what we have on the browser, and probably just go ahead and hide this. So here we have FFF8, FFFF, 00, and FFFF, the first 4 entries here. And what did we get here? So FFF8, FFFF, 00, and FFFF. So that looks pretty good to me. So I think now we have our fat saved up. What we need to do now is move to reading the root directory. Right, so let's start by reading the root directory. I guess first of all, we will need to know where it starts. And I think we already have something for that. Or actually, no, we can just do this. So BPB reserved sector count plus fat size multiplied by the number of fats will basically land us on the root directory. Since we are in FAT16, we don't need to check that we have a root directory somewhere else. So let's do root there start. And this would be BPB reserved sector count plus so fat size times BPB table count, and that would lead and that would land us directly on our root directory start. So I guess the main question here is to know what the root directory looks like. So from what we've seen already when we've printed the root there count or entries count, we know that we can have a maximum number of root there entries count entries in the root directory. But the question that remains is, what does an entry look like? So let's go back to Katai to see. Right, so here if we click over on root there here, we can see that we have records. And if we just collapse them, we can see that we should have 512. Yeah, 512 starting from 0. That's good. So if we go here, we can see that this is our root directory. So if I just take one record here, it would be just these 2 lines. Right, and what we are seeing here is basically the files that we have, files and folders, because folders are, or directories are also files, that are in our root directory. Right, so here we have EFI system, which is the partition name or the root directory name. Here we can see that it should have, volume ID is true. So basically we have attributes on every entry, and every entry should be 32 bytes long. So for every entry we have this byte here that's attributes, and we have basically these flags that can be set from those attributes. So if the flag volume ID is set to well, the bit that corresponds to this is set, then we know that this entry here corresponds to the volume ID for this partition. Right, and of course here we have some reserved, some reserved bytes. We have some dates for the last time we've wrote to this file, and we have the start cluster and the file size for this entry here. Well, this first entry is not really interesting since it's a volume ID entry. So if we look at the next one here, so it's this one here, and this one here is directory is set to true in the attribute flag. So this means that this entry here is a directory called BIOS. So we can see that the file names in FAT16 are limited to a total of 8 bytes for the file name, plus 3 bytes for the extension. That's why extensions usually have 3-letter variants. Like for example, GPEG has the GPG variant, just so that it can fit file systems that only allocate 3 bytes to extensions. Of course, here we can see that the start cluster is 3. So to basically see what we have inside this of this directory here, we need to basically go to cluster 3 and read from there until we basically read the whole thing. And we are going to use our file allocation table for to read the next chunks. So this is the first chunk here. And we know we don't have a file size since this is a directory. If we look at the next one though, this one is a file that I've added. So we can see that all the flags are set to false. We don't really care about archive. And this file here is a file that I called boot.con, which will be our config file that we are trying to read. We can see that it's it starts at cluster 12 and it has a file size of 6. So if we just go back here and in the build directory, I have this file here called boot.config with the const hello. So hello is 5 bytes plus the null byte, so it's 6. And if we go here to the make-file, I've added this line here to copy boot.config to boot.con, which is what we're seeing on the disk. Right. And I guess the other entries are just 0, so they are empty. Right, so I went ahead and created this directory entry struct. and now we can go back and use it. So here we have the root start, and I guess we can just go ahead and allocate for our root directory. So it will be a pointer or a collection, an array of their entry, and call this root directory. And here we are just going to do their entry pointer and pm alloc. So what do we need to allocate? We need to allocate size of their entry times times the, actually it's something that we've already done somewhere here. There we go. So this 32 bytes here would be the size of their entry. So let's check. Yes, it's 32. So basically here what we need is this, and we can just go ahead and use that here. There we go. And we can go ahead and just add the type, which is, again, a map reclaimable. And now that we have this root entry here, so we can just go ahead and issue a read for it, and we can start at root their start, and we'll pass it the pointer, so root directory, and of course the size of the root directory is root dir sectors that we've already computed before. And of course here we will need to drop this to U16, which is fine. Actually, we could drop it to U16 here also. And also here. Oops. There we go. And here also. There we go. Well, that should be fine. So now that we've read our root directory, so we should probably just go ahead and print the first entry, see what we have in there. What should we do here? We should probably print the attributes for sure. We should also probably print the issue with the name is that we don't have a zero termination. So if we want to print, we need to put it in a buffer, a zero terminated buffer before that. But we can probably just go ahead and print at least the attributes, and actually let's print the file name also. Right, so here we do something like this, and we will call this file name, and this will be, so we know that we have 11, so this would be 12. And what we will do now is we will do, so mem copy, and we will copy to so file name from root dir name, and we know that the length is 11 for that. So here we go. So I guess now we can just print file name, and let's see. And this would be just %s. There we go. Normally with this we should be fine. So let's build this and see what we have. Actually, before we do that, let's not have problems, okay? So let's properly set the last item here to 0. And now that I look at this root, their start here is relative to the start of our partition. So we will need to bump that to boot partition. So what was it? Start LBA. There we go. Plus that. And of course, this will need to be cast to U32. So, all right, let's now finally build it and see what we have. Okay, so here we clearly have a partition name, EFE system, which is the one that we've expected, since that's what we see here. EFI system. Right, so now let's just try to go over the partitions and print all the names. Right, so let's do while, and before that we probably need to take an entry here. So partition entry would be entry, and it will be root there, and while entry. So what would be our check? I guess we could check attributes while attributes not equal to 0, since we have no attribute 0 in our attribute list. We can go ahead and do something like this. Yeah, that would be fine. I guess we'll just need to remove this and replace it with entry, and that would be fine. Do something like this. And we should probably also do so bool is directory, and this would be entry, attributes, and some attributes. So let me just take a look at the spec. Right, so I've created these defines here for the attribute, and while doing that, I actually found something very interesting in the spec. So here, if we go down, we can see that their name 0. So if the first byte of the name is 0, it indicates that the entry is free, but it also indicates that everything below that is free. So we can use this as our loop condition instead of just checking the attributes. Right, so let's do that. Where was I? Right, so here we can check if name at 0 is different from 0, and here is there, we'll basically say file attribute directory. So if this is a directory, this bit here would be set, and we'd know. And here we can just do type and something like this. Here we can do a bit of magic. Is there, if it's a directory, we can do this. Otherwise, we should turn just file. All right, let's see what we have. Okay, yeah. Probably we need to increment the entry. Right, Let's see now. Oh, cool. So here we go. Let me just zoom in a tiny bit here. So we have 3 entries as expected. We have, okay, well, the first one is obviously wrong because this one is not a file, it's the volume ID. But this one here is correct. So this is a directory that we have inside our file system. And this one here is a file. We are now going to try to read. Okay, so before we start reading files, we might want to just do a bit of cleanup here. So this thing here, we don't really need it anymore, at least for now. This one also. And here we have our main issue is that we have allocated quite a bit of memory here for our BIOS block, parent block, and the FAT and the root directory. And we don't really want to keep doing everything in the same function here. So what we are going to do, what I'm going to do is I'll probably just create a struct here to hold those. So what do I call this? Just go fat info. And inside this fat info here, I'm going to keep a pointer to the BIOS parent block, and I'm going to keep also a pointer to the FAT, and this would be U16 pointer, and also going to keep a pointer to, so the entry pointer to root directory. There we go. So with this, now we should be able to return our FAT info. Should probably name this something else, but nothing comes to mind for now. So FAT info it is. And here we are going to do FAT info. What do I call this? Just call it result. And we'll initialize it. And then we are going to return result. There we go. Right, and here what we have is our BPB would be BPB. Our what's that called? FAT would be FAT, and our root directory would be root there. Oh yeah, obviously this should not be a pointer. So that would be fine. And here what we are going to do is we are going to just go somewhere here and create a FAT info. Okay, so we probably need to do a bit of cleanup here. So this one would need to move over here. And of course we need partition type. So what's partition type? It's this thing here. Goes there. And then we need to know about the this thing here. So just grab that. There we go. And now let's see, what else do we need? Okay, so now we should be okay. At least I think. Right. There we go. Okay, so with this, we have our cleanup done, and here we can just do fat fs info equal to whatever we get from there. And now we can go ahead and create our or read our file. So first of all, we'll try to take this easy. We will try to write a function that only reads files from the root directory, because that's the easiest thing we can do. And then we'll see what we need to do for reading files pretty much arbitrarily from the file tree, given some sort of path. All right, so here I'll just create this read file from root, and here we'll take a U8 pointer, file name, and let's get cracking. So first of all, let's get the length of a file name. So user2 file name length or len, and here we just call strlen. What was it? Yeah, file name. There we go. So here it says that it's not const. Of course, we can set it to const. We're not going to change that. And of course, it wants a I8, so we can do that also. Right, if the file name is too large, so if file name length is greater than 11, then we should just basically panic. So let's print something like error file name too long, something like that. And we should probably just spin. I should probably refactor this error and spin thing into a helper function. Note to myself. Right, so here we know that we have a file name, so we should just traverse the directory. So let's create our dir entry pointer entry. And this is equal to fs info dot root directory. I think that should be fine. And here we go. So while this name at 0 is not 0, we should do if. So we know that we are looking for a file. So anything that is not a file, we can just skip. So if entry attributes and file attribute, so volume first of all, or entry attributes and file attribute dir, then we just continue. Yeah, well, I actually want to use continue, so let me just get rid of this and change this to a for loop. So for, we're not initializing anything, and entry name of 0 is not 0, and here entry plus plus. Right, so here we can just do continue now. It should be fine. Right, so if the file is a volume or an attribute or a directory, we just skip it. I think we should also skip so hidden files, attributes, and file attrib hidden. And actually just want to go here and see. So I think we should also just skip system, but I don't think we have a system entry for now. So let's ignore that. And now we need to do so stir n comp between the name of the entry and the file name that we've received. And of course, here we know that it's 11, and we know that this should be 0 for these to be the same. And this one here, I guess there's no constness, so let's force it to be const. Right, so if we find the file, then we should probably just read it. Otherwise, we should return something. So I guess if we find the file, we should just break from the loop and read after that. Yeah, but how do we know that we found the file? That's the question. Right, so I guess should do something like actually, there we go. Right, so here should probably just do something like yeah, we could have kept that there. Found is true, and then break. Right, so here if not found, so what do we need to return here? I think the goal would be to return some sort of void pointer, which is basically the contents of the file read somewhere in memory. And here we're just going to do return, I can type, return null. Otherwise. So now we know that we have a valid entry, so we should basically go ahead and read it. And the way we are going to read something from basically an entry from memory is we are going to so we need something that's we call this current cluster, something like this. And what do we need to do here? So current cluster would be basically, it would start as first cluster, and we will need to read some, or basically we need to allocate some memory for that pointer that we have. So let's allocate some memory here, void pointer contents. And this would be pm alloc, and we will allocate. So the size would be entry file size, and the type would be reclaimable also. Right. I guess I want to add something else here. So if not found, or if the entry file size is 0, then we just return null because there's basically nothing for us to do. Otherwise, we want to read the clusters one by one. So we will do a loop here. So let's read the cluster to contents. And for that, we are going to do, basically we are going to issue BIOS read sectors. And here we know that the star sector would be our first cluster, or it would be, so let's do this. Let's create a U32. cluster sector equals, and this would be boot partition dot. I guess we need to get the boot partition also here, or at least we need to have the boot partition as a global here. So let's do that. Actually, can do it here. I guess I think I've called this partition info and boot partition. There we go. So if we come back here, yeah, that should be okay. And this would have the start LBA of our partition. And then we can just basically take that and add to it the current cluster. But we need to know where in the disk image this cluster falls. So for that, we need to do a bit of computation. So there's a very important piece of information here that is pretty much hidden unless you go looking for it. So the first data cluster in the volume is cluster number 2. So given any cluster ID, we need to basically subtract 2 to get the actual ID of that cluster to go looking for it on disk. So let's do a simple computation here. So given our boot partition start and given the current cluster, of course, as I said, -2, and right, so that times the so we should time that with the boot. So where do we have that? Do we have that in file fs info.bnp? There we go. So here we need bytes per sector, and we need fat fs info bnp, and we need sectors per cluster. There we go. So with this, normally we have actually what I'd like to do is just go ahead and create something here that I'll call data sector start, or data start sector, something like this. And this would be boot partition start plus the fatfs info, and here from the BPB we are going to take the reserved sectors count, and to that we will add the basically the fat size. So get fat size, and from of course we'll pass it boot, or rather it's fat fs info BPB, and the fat size multiplied by the fat number BPB, and table count. Right, so this, and we can actually just hoist this out of the loop. And we should probably just do some conversions here. So this one here needs to be U32. And here we are actually just going to remove this or change that with data start sector plus. There we go. Okay. So there's just another thing here that I need to think about, and that is this in terms of sectors? No, it's not. So I think we can just get rid of the bytes per sectors. So we can have the whole thing in terms of just sectors. So here, if I right, so here we will have, actually I forget why I called that cluster sector. And here the destination would be did I allocate? Yeah, I called it contents. There we go. And I'll do contents plus index. Yeah. And here the count would be, well, we read in one cluster, so it will be fatfs info bpb sectors per cluster. There we go. So now we need to define this index, and I'll just go ahead and define it here. And this index will be a U64. U32 would be fine. Index. And it'll be 0 at the start. This index here will let us be able to write into this page or into this set of pages that we've allocated here at some given index, basically. And what I'll do here is I'll also change this to be just a byte pointer to make life a bit easier. Right, and here, of course, we are going to just add a cast. Right, and that should be it. So now that we have read this sector, and obviously here we need two things. We need first to do the return, and we're just going to return contents. And here it will yell at us because we need to add the while condition here, and the while condition would be while current cluster is so here we need some condition to stop, and for that we will go looking for it in our documentation here. And here in the comments we can see that for FAT16 we can go from so basically 2, which is the first cluster, to max plus 1. And these values here, so FF7F means that the cluster is defective, so we don't really care about that. But FFF8 to FFFE are reserved and should never be used, and FFFF means that the we have basically reached the end of the cluster chain for this file. So we should probably just have a condition that says that if we are less than or if we are higher than FFF8, we consider ourselves done. Otherwise, we continue looping. Okay, so here, while this cluster here is less than, so if this is less than FFF8, we go again. But before we do that, we now need to, so we've read this cluster here, so we need to go to the file allocation table and go to the index that we have here in the current cluster and read what the next cluster would need to be. So let's do that. Right, so current cluster here will basically just be so fat fs info dot fat, and here we basically index it with current cluster, and that should be our file. Right, so here we should probably just add this, and we'll be fine. So let's give this a spin and see what we have. If we go to main, if we go somewhere here and we do, so we know that it's just bytes, so let's do that and call this config file. Well, first of all, let's create the config file name. This would be boot, and we know that there are so 11 characters, so I need to put in 4 spaces and then con. There we go. So once we have that, we can do u8 pointer config equals, and actually we need to make this function here available from there we go. And with this, we should be fine. Okay, so here we can go ahead and do read file from root, and we have config file name. There we go. And of course, this can be const, and it can also be i8 since you insist. Right, and we can also go ahead and do a simple printf of config equals, and just do %s and print config. There we go. All right. So let's give this a compile and see what we have. Right, so something went wrong here. This is not really what we expected to see. So let's take a peek and see what we have here, what the problem is. So let's go to GDB and target remote. There we go. And we'll also load the elf file for symbols, and we'll break at cmain, and we'll continue. Okay, so we have our breakpoint triggered. So now I guess we can just set another breakpoint for so line 12. Okay. And now we are going just to step into that and see what we have. So file name length is is 11, so that should be fine. Let's keep stepping into this. We load our directory entry, so let's just check that we have a correct entry here. And it looks okay. Yeah, it looks okay. Right, so let's go ahead and continue here. Okay, so we have found our entry here. And I guess found should be set. Okay, well, it's optimized out, but it should be fine. And now we are going to allocate memory and do this whole computation here for data sector. And we should, there we go. So now if I just print data sector, start sector, there we go. So 2092, that doesn't look good. Right, so that doesn't look very good. So currently our first, or our boot partition, we know that it's at 800. And to that, we add the basically the size of reserved sector count. Actually, we can just print out so fs info dot bpb should deref that. So what do we have here? So the reserve sector count is 4. So to that we should add so 4 times 200. We are in hex mode, by the way. And then to that we add. So what did we add to that? We add the fat size, which is the table count times the actual fat size, or actually, yeah, this line here is the table count times the actual fat size. We know that we have so 20, 0x14 sectors or clusters, no, sectors per fat. So that's this. So that should bring us to 3800. There's possibly something wrong here. Oh, okay. I think I know why it is wrong. I think we never skipped the root directory, I think. So let's go back and see what we have. All right, so let's add to that get root directory sectors. Of course, we pass it this.bbb. And with this, we should probably have the correct values now. So let's just rebuild this. And let's just rerun it. Oh, and what do we have here? Probably need to get rid of this. Look at what we have here. We have exactly the content of our file. So we have succeeded in reading a file from disk. So let's do something here. Let's ensure that we are reading whatever we have on that file. And it's not just some fluke. Right, let's regenerate our disk image and reread this thing. And here we can see that it's still working. And with this, we have read our config file from disk. Well, that was it for today. Here in the roadmap, I've marked both the FAT16 file system and reading config file as partially done, because for the FAT16 we still cannot write to the file system. We can only read from it. And we can only read files that are in the root directory for now. So there's a bit of work to be done. As a bit of an announcement, in the next 3 to 4 weeks, the videos will get quite a bit shorter. Otherwise, I will just not be able to fit them into my work schedule. I might even skip one of the weeks. So I hope we're cool. Otherwise, as always, hit like, subscribe, and go touch some grass.